Welcome to Hartman Math. This is lesson 9.7, probability. So if you're about to head off to Vegas, take some notes. So if we've got an uncertain result, we're going to call that an experiment. And the possible results are outcomes. And if we list all of the possible outcomes, we've just listed the sample space. So for example, number 1, part A, we're going to draw a marble from a bag that has in it 1 red, 1 white, 1 blue marble. So the sample space would be all the different possibilities of pulling out a marble. We could pull out a red, or a white, or a blue. So the sample space is red, white, blue. We're listing that in set notation. What if we draw 2 marbles? We could get red followed by red, red followed by white, red followed by blue. What else? White followed by red, white followed by white, white followed by blue, blue red, blue white, and blue blue. So in that case, 9 different outcomes in the sample space. That would be called the size of the sample space. So the probability of an event happening in an experiment is the number of ways that the event can happen divided by the number of outcomes in the sample space. So for example, if we spin this and we got 2 spins, what's the probability that both spins are odd? Well, the first thing we might look at is how could that happen? So what are the different ways? What could we get on the first spin? A 1. And what about on the second spin? A 1. Or a 1 and then a 3. Or a 3 first and then a 1. Or a 3 and then a 3. What about, so that makes 4 different outcomes in the event. The sample space is 1 then 1, 1 then 2, 1 then 3, and so on. 2 then 1, 2 then 2, 2 then 3. So there are 9 different elements there in the sample space. So our probability of both odd, 4 out of 9 is our probability. A reminder that probability has to be between 0 and 1 inclusive. Could be 0 if it can't happen, could be 1 if it is a certainty. Example number 3, find the probability of an event. Johnny is playing craps in Vegas. Rolling a 7 or 11 is called a natural winner. What is the probability that his roll is a natural? In these dice problem where there's 2 dice, I like to think about one dice of one color and 1 die of another color. So if we look at how could we get a 7, maybe if we have a white and a red or something like that, a white 1 and a red 6, so that we kind of get all of the possibilities. So red 1, white 6, that gets us a 7. What else? 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2, 6 and a 1. Now that's getting the 7. How can we get an 11? 5 and a 6, 6 and a 5. So how many events are there that would be successful for our natural winner? We got 8 of them. What's the size of the sample space? Okay. Well, if we think of this as 2 events, how many ways can the red die be rolled? How many ways can the white die be rolled? Thinking back to our counting principles from the previous lesson, 2 events, 6 in each, 6 times 6, 36. So our probability is 8 over 36, which reduces to 2/9. Now you might think that's not very good odds for winning, but there's more to the game than just that. So for example, checkpoint Okay? If your roll is a 2, 3, or a 12, that's called craps, and you lost. So, go ahead and find the probability of that happening. So the ways that we can get it, well, there's a 2, there's a 3, there's a 12, 4 possible ways of any of those 3 outcomes. So 4 divided by 36 is 1/9. So you might think, hey, that's pretty good. 2/9 of winning, 1/9 of losing. Well, obviously there's a lot left over if one of those 2 things doesn't happen. It's like, what if you get an 8 or whatever? So there's other rules involved in that game. Example number 5, random selection. Class list is given. You got 20 study problems. And of those 20 study problems, 10 are going to be on the exam. If a student knows how to do 17 of the 20, and they're in the study guide, what is the probability that the student will be able to correctly answer all 10 questions on the exam? So if we think back to our counting properties, obviously we've got a lot of numbers here to choose from in test problems. Does the order matter of our 20 questions? Not really. So it kind of sounds like a combination. So the number of ways of getting all 10 questions, okay? But you got to get them right. So think of it as a combination. How many out of how many? Well, if we're talking about the ones that we can do right, we have to get 10 of them. Chosen from how many? Not the 20, because you don't know how to do all 20. It's 10 chosen from the 17. Now, the size of the sample space, we're going to get 10 of those questions from the 20. So the size of the sample space is 20C10. And if we now divide those, number in the event divided by the number of the sample space, there's our probability. It does reduce to 2/19. So those are the chances, if you know how to do 17, that you're going to be able to get all 10 right on the test. Mutually exclusive events. We've got 2 different events, same sample space. They are mutually exclusive when those 2 events do not have any outcomes in common, in which case the intersection, or the probability of the intersection, is 0. Example. So in a class, I'm going to choose at random a freshman. Event 2, choose a student that's in AP Calculus. So I would say most years in that AP Calculus class, there are no freshmen. So there's no student that's a freshman and here. So the overlap, the intersection, there isn't any. Okay? No Sheldon Coopers, if you're a Big Bang Theory fan, that's taking AP Calculus as a freshman. So the probability of the union of 2 events, if A and B are events in the same sample space, the probability of A union B, and a lot of times in terms of language, we might say the probability of A or B would be the probability of A plus the probability of B minus the probability that both happen. Now, if they are mutually exclusive, this is 0, as we said here. So it's just probability of A plus the probability of B. Example. We draw a card from a standard deck. What's the probability that the card is an ace or a face card? So when we talk about aces, we got ace of clubs, ace of hearts, ace of spades, ace of diamonds. There's 4 of them out of the whole deck of 52 cards. Yes, we can reduce it. A lot of times we might wait till the end to do that. Probability of a face card. Now that's a little bit of an ambiguous term here, because really depends on what you're talking about. But in literal sense of a face card, it's a card that has a face on it. So the jack has a face, the queen has a face, the king has a face. So 3 of those, 4 suits, we're talking about 12 out of 52. In some games, you may talk about a 10 being a face card because it has the same value. We're not doing that here. We're just saying these are our face cards. So the probability of drawing an ace or a face card, well, these are mutually exclusive events because there is no card that is both an ace and a face card. So we could just add those up, reduce it, and we've got our answer for part A. Let's look at part B. What's the probability that the card is an ace or a heart? Again, ace, we just said there's 4 of those in the deck, 4 out of 52. Hearts, okay, so 1/4 of the cards are hearts. We've got the ace, the king, the queen, and so on, all the way down to 2. There's 13 of them, but these are not mutually exclusive events. Are there any cards that belong to both of these? There are. So we're going to need to add them together because the intersection, there's one card that's in both of those. It's the ace of hearts. So that's the intersection. So the probability of getting an ace or a heart is this plus this minus this. Because what happened in here is we counted the ace of hearts here and we counted the ace of hearts here. We counted it twice. That's why we have to subtract one out to remove that double count. And there's our answer. Well, let's reduce it. 4 out of 13. Independent events are events that when the first event happens, it has no effect on the subsequent event, the second event. If that's the case, and then there's the key word, we're talking about the probability of A happening and B happening, we're going to take the separate probabilities and multiply them together. So in a probability sense, and signifies that we are going to multiply. All right, example number 9, probability of independent events. A bag contains 3 Snickers, 5 Milky Ways, and 11 Three Musketeers. What is the probability that you select the 3 Musketeers, put it back because it's gross, and then select the Snickers? So these are independent events because of the putting it back. So what you pull first does not affect, since you're putting it back, it doesn't have any impact on the probability on that second event. So what's the probability of getting a 3 Musketeers on your first grab? Well, there's 11 of them, and there's 19 candies. So it's 11 out of 19. We put it back. Now we grab a Snickers. Since we put it back, there's still 19 candies in the bag. 3 of them are Snickers. What's the probability that this happened and then this happened? We're going to multiply them together. Now, if we didn't put it back, then the second probability is dependent, and this part would change. We'll still be able to multiply them together, but this second probability is going to change because there are no longer 19 candies in the bag. One idea that can help us out is the complement of an event, which essentially means that event will not happen. Sometimes that's easier to think of or calculate than it will happen. So basically the way we look at it is the probability that something happens plus the probability that it does not happen has to equal 1. Because it either has to be one or the other. So it has to be a probability of 1. And if we then use that idea, then the probability that it didn't happen is 1 minus the probability that it did happen. That's our formula. All right, so example number 11, probability of a complement. The probability that Claire gets asked out by Jeremy is 0.35. What's the probability that she doesn't? Okay, so doesn't is the complement to does, since the opposite. So 1 minus 0.35 is our probability of 0.65. Continuing on with that same idea of a complement, let's say I have a substitute for the honors pre-calculus class. There are 22 students in the class. 19 of the 22 students are good kids. Find the probability that, if asked, to send up 4 students to be interviewed by KCRA, Channel 3, that our substitute randomly selects 4 good kids that are going to represent our school well. How many ways can we choose that to happen? Remember, we have to choose 4 good kids. Now, it doesn't matter, let's say Tim is a good kid. It doesn't matter if Tim is the first one to walk out the door or chosen or the third. So again, if order doesn't matter, we're going to think of combination if we've got multiple things happening. And we're selecting multiple people here. So probably going to be a combination. So, got to choose good kids. So we're going to choose 4 from how many? Well, it's not the 22 because they're not all good. The 19 are good. So we have to choose the 4 from those 19. That's the number or the size of our event. Now, what's the size of the sample space? That anything could happen. Now we're talking about all the kids. We're still selecting 4 kids from the 22. So if we divide those, 2204 over 385 is our probability, a little bit more than 50%. Part B, find the probability that if asked, send 4 kids, she sends up 1 bad kid. Still 4 kids going up, but 1 of them is bad. Okay. So the size of the sample space. You got to send 1 bad kid. Well, I'm not just sending 1 bad kid. That means that there have to be 3 good kids. So those 3 good kids are chosen from how many? 19. And means multiply. 1 bad kid. 1 bad kid is chosen from how many? Well, according to the numbers here, there's 3 bad kids. So 3 choose 1, 3C1. So good kids, bad kids, total of 4 students. 2,907. We've already talked about the size of the sample space. So that probability is 153 over 385. Part C. Find the probability if asked, she sends at least 1 bad kid. At least 1 bad kid. So that means it could be 1 bad kid, it could be 2 bad kids, it could be 3 bad kids. I don't think it'd be more because there aren't more than that, okay? So even though we're sending 4 kids, there's only 3 bad kids in the class. So it has to be one of those things. So we could find all of those. And remember, so we're talking about 1 bad kid, or 2, or 3. Every time we say an or, that's going to be an addition. We could do that. But it might be faster and more efficient to use the complement. What's the complement to at least 1 bad kid? So not 1, not 2, not 3. How many bad kids? 0 bad kids is the complement to this situation. So if we found that, which should be actually pretty easy, because I think we already did that in part A, since we're talking about complement, we could subtract that answer from 1 and have our answer this. And that's how we could use complement. So we're talking about 1 minus the probability of no bad kids, because we're talking about that being the complement, which we already found. So that's going to be 181 out of 385. And another example 11, where we might be using complement. Where the probability that Kyle gets a quiz question correct is 96%, or 0.96. What is the probability that he misses at least one question on a 10-question quiz? Well, if we tried to do it straight from there, it's a challenge. Because missing at least one means missing 1, or 2, or 3, or 4, or etc. And that's really very complicated, because then you're talking about, well, if you missed 2, is it questions 2 and 8, or is it 3 and 7, or 1 and 9? It gets really complicated. Whereas the complement's a really basic idea here. What is the complement to missing at least one question? It's not missing at least one question, which means getting them all right. And that's going to be a much easier thing to do. Now, this is a fundamental counting principle problem. There's 10 questions, and that means there's 10 events. Each question represents an event. So if we're talking about getting them all right, what's the probability that Kyle gets the first question right? 0.96. What about the second question? 0.96. And the third, and the fourth. And since it's and, we're going to multiply all of those together. So the probability of getting them all right is 0.96 to the 10th power. And therefore, the complement, the probability that he misses at least one, is 1 minus that probability, which is going to be about 33.5%. That's it for today. See you next time.